Here's the answers to the practice quiz on moles. If you can do this, you can do anything, right? Question 1, which of the following statements is false? It should be the third one listed here. 1 mole of sodium contains more particles than 1 mole of lithium. Well, 1 mole of anything is the same number of particles. It's that magic 6.02 times 10 to the 23rd particles. Kind of like a dozen of anything means you have 12. A mole of anything is just a lot more than 12. Or I should say option 1 is correct. Option 2 is correct. I mean, a mole of different substances will have different masses. We can find that mass on the periodic table. We call it the molar mass. And so, yeah, when I look up sodium's molar mass, it's about 22.99. Lithium's molar mass is about 6.9. And so their masses are different just because the atoms are different. Lithium atoms are smaller. They only have 3 protons, and sodium atoms are bigger. They have 11 protons. And so, yeah, I mean, the size of the particle, the mass of the particle, that's going to be different. But it's the same amount when I have a mole of each element. Molar mass, then, of an element is just found on the periodic table. We can use those periodic table masses in grams, but it's silly to say that 1 atom of oxygen weighs 16 grams, like 16 paper clips. Are you crazy? That'd be a mole of oxygen. And so if we have a compound, we can still find its molar mass. We just have to do a little math. First thing we have to do is write the formula, because I need to know like how many atoms of each element are in my formula. And so I've got iron. The Roman numeral 2 is just telling me the charge on the transition metal when more than 1 charge is available. And then phosphate, the ATE is a polyatomic ion. The 8s and ites are on that chart. It's on page 98. So you can find this guy and all other polyatomics on page 98 in your book. You will have that chart anytime you take a summative. If you forget your book, it'll be linked in the assessment so that you can look up those polyatomics. The IDE ending would have been like regular phosphorus, like phosphide, sulfide, chloride, oxide. Those are just the regular negative ions. But the 8s and ites, those will be polyatomics, many atoms that all have a charge. Now there's still only 2 charges. There's a positive and a negative, and I need to make this compound neutral. So you could be a charge balancer, where you're saying if I have 3 iron, that gives me 3 times 2 for a plus 6. If I have 2 groups of phosphate, each is minus 3, that gives me a total charge of negative 6. On the flip side, you may have been a crisscrosser, and you still have to find those charges, but then you can crisscross the numerical charge. You don't have to bring down the plus or minus. And you can get the ratio of ions that way as well. All right, so first thing is to make sure that you have the right formula. Then I'm ready to find the mass. So I've got some iron. I find the mass of a mole of iron on my periodic table. But if I had a mole of iron 2 phosphate, there would be 3 moles of iron atoms. I got to multiply. Then if I have a group that's in parentheses, that 2 means you have 2 groups of phosphate. So you've got 2 of everything on the inside. So I'm going to have 2 phosphorus and 8 oxygen. So I find the mass of phosphorus and oxygen and multiply. From there, we just have to add. Just going to plug it in my calculator and add them all up. If a question says to show work, calculate the molar mass, show your work, then this is what we want. I want to see what individual masses did you use, what did you multiply by, and we need to see your formula. And if you wrote the formula wrong, you could still get some partial credit if you found the mass correctly of the formula that you did right. Or vice versa, you wrote the right formula, but maybe you accidentally forgot that there'd be 2 phosphorus and 2 times 4 for 8 oxygen. Well, I can give you something because at least you wrote the formula correctly. Then when I'm ready to do a mole conversion, you start with the amount that you're given. Somewhere you'll be given a number, a unit, a substance. This is 35 grams of hydrogen sulfide. All right, so I got the formula. There's going to be 2 hydrogen and 1 sulfur, so that my compound is neutral. From there, I like to start with the units. I was given grams, and so I know I want to get rid of grams. I'm going to set up my proportion with grams on the bottom. What you want goes on top. How many moles? Oh, okay, moles. I'll put that on the top. Then I can go in and put the numbers in. Anytime you see the unit mole, the number is going to be a 1. Anytime you see the unit grams, it's going to be off your periodic table. So this guy here is from my periodic table. Now I just had to add it up. So that 34.076, that's the molar mass of H2S. Now if the question is asking you to calculate moles, then this is the work that I need to see. Show me the amount, show me the substance, the formula that you used, and then show me your proportion. Did you cancel grams and switch it to moles? Show me the mass that you used. I can tell if you have it set up right, but maybe by accident you've just found the molar mass wrong. That 34.076, that would have just been 2 times hydrogen plus 1 sulfur, right off my periodic table. Seems about right, because sulfur is like 32-ish, and each hydrogen is about 1. Like about 34. Then when the number's on the top, I would multiply, but here when the number's on the bottom, we divide. And now this answer seems reasonable. 35 grams is my sample size. Every 1 mole is 34 grams. So I should have a little bit more than a mole. This would be a multiple choice question that I could just set up, and even if I didn't have a calculator, I could pick the reasonable answer. There's only one that's reasonable. All right, so it's all about setting up these proportions and getting the units right. We're obsessed with our units. So I have 6.05 grams of carbon. It's not good enough just to put the number. I got to say what it is. Because then the unit that I started with, grams, is going to go on the bottom. I want it to cancel. The answers are all in moles. So if I want to convert it to moles, that goes on the top. And again, anytime I see mole, it's going to be a 1. Anytime I see grams, it's going to be off my periodic table. If it's an element like this, I can just look it up. 12.011. And again, this number is reasonable. I have about 6 grams of carbon. 1 mole would be 12 grams. I have half a mole, right? There's only one number that's even close. Now here I've got 9.03 times 10 to the 24th molecules of carbon tetrachloride. Here's one of those covalents that has the monoditride. It's equivalent to how many moles? Okay, so I've got my 9.03 times 10 to the 24th molecules. I want that to cancel, so molecules went on the bottom. It's equivalent to how many moles? I put moles on the top. Then anytime you see a mole, it's a 1. Anytime you see atoms or molecules, like a representative particle, it's 6.02 times 10 to the 23rd particles per mole. This particle would be a molecule. I've got multiple atoms bonded together. All right, so if the number would be on the top, I would multiply. Again, here the number is on the bottom, so I'm going to divide. Now, you can plug this in your calculator different ways, but I would for sure practice before I get to a summative, just so that you know you're entering scientific notation properly into your calculator. So you've got two options. Option one is for those that are obsessed with the caret key. So you might be plugging this in your calculator as 9.03 times 10, and then you got that little like caret key, 10/24. You might want to put that in parentheses if you're going to do a calculation with it, because we want our calculator to know that that is one quantity. 9.03 times 10 to the 24th. Then I could type in divided by, and then I'm going to do kind of the same thing, but again, it's this quantity that I want to divide by, so you might need to put it in parentheses. 6.02 times 10 caret 23. You could plug it in like that. Another option, you've got a second function on your calculator that's like this little EE key, and that is actually meant to be used for scientific notation. So you could plug this in as, 9.03. Then you just hit like the second function and you should have a little EE key. And then all you have to say is EE23, or 24 in this case. You don't need parentheses because your calculator knows if you use that EE key that you mean for that to be a number in scientific notation. It knows that you mean for it to be one quantity. So you probably don't even need to put that in parentheses. Then I could say divided by 6.02, and then same thing, hit that EE key, 23. Also, if you're using that EE key, you don't need to say times 10. It already knows that. The EE is specifically meant to be used for scientific notation. Now, the other option is to use your noggin and maybe your understanding of scientific notation. 10 to the 24th is like 1 power of 10 greater than 10 to the 23rd. So you could flip this decimal spot one place, and you could do like 90.3 divided by 6.02. Aha. Depending on how well you know scientific notation, any of those will get you the right answer. About 15 moles. Awesome. All right, what if we have 3 moles of calcium hydroxide? So the unit that I have is moles. Calcium hydroxide was CaOH2. 2 groups of hydroxide. So I was given a number in moles. I want to put moles on the bottom so it cancels. We want to know how many molecules are in the sample. So the unit that I want goes up on top. I want it in molecules. Anytime you see a mole, it's a 1. Anytime you see atoms or molecules, it's the 6.02 times 10 to the 23rd. This time I'm going to multiply across. Now that totally makes sense because like 3 times 6 is 18. So 18 times 10 to the 23rd is the same as 1.8 times 10 to the 24th. What mass is equivalent to 0.332 moles of beryllium? So I've got a number. I've got a unit. It's in moles. I want to cancel moles. And I want mass, which would be grams. So I put my units in first, and then I fill in the numbers. Whenever you've seen a mole, it's always been 1. Whenever you see grams, it's always off the periodic table. With an element like beryllium, I can just look it up. I'll multiply across and see if this number makes sense. I'd say so. It's about a third of 10.8. I think that seems about right, huh? About 3-ish. The other thing that I should note too is that on the top one with calcium hydroxide, if I wasn't using grams, I kind of didn't even need to find the formula, did I? The only time that I need to know the formula is if we're dealing with grams, because the mass will be different depending on what the substance is. But this relationship, that would be true for 3 moles of anything. All right. A student has 6 grams of iron in the lab. Oopsies. Carbon in the lab. Looking at the wrong one. For our reaction, the student needs the same number of magnesium atoms as carbon atoms. How many grams of magnesium should the student use? Okay, so these two questions here are eventually where we're going to use this mole stuff a lot. Chemical reactions often occur at very specific ratios. 1 atom of this for 1 atom of that. Every 1 atom of this needs 2 atoms of that. The ratios are very specific. But it's hard to really go in the lab and count atoms. I mean, it's nearly impossible to count atoms of carbon and then count a sample of magnesium that has the same number of atoms. But moles is a unit that represents a quantity of particles. If I have samples with the same number of moles, they'll have the same number of atoms. Now, there's different ways that you could have set these up. And I'll show you another option that totally works. But this might be the easiest way to go about these. Take that 6 grams of carbon and turn it into moles. It makes total sense that it's about half a mole, right? I've got 6 grams of carbon. Each mole is 12 grams. I have half a mole. Well, if I have half a mole of magnesium, they would have the same number of particles. The molar mass of magnesium is about 24 grams, so half a mole of magnesium is 12 grams. I mean, look at these two. It makes total sense. The molar mass of magnesium is about double the molar mass of carbon. So 12 grams of carbon, 24 grams of magnesium, same number of particles, 1 full mole. Well, here we're just going to half that. If I had 6 grams of carbon, that's half a mole. 12 grams of magnesium is half a mole. If you've got the same number of moles, you've got the same number of particles. Which you could do again with the second question. What mass of copper has the same number of atoms as 6.41 grams of iron? Just get these guys into the same number of moles. Start with the iron. If I have 6.41 grams, I can cancel grams, put it into moles. The mass comes right off my periodic table. When the number is on the bottom, I divide. 0.115 moles of iron. So then if I just say, all right, then let's use 0.115 moles of copper, the samples have the same number of atoms. But now I want to turn that back into grams because often in the lab we measure in grams. So this time I want to cancel moles and put it in grams. So grams goes on the top, and I'm going to multiply. That 63.546 comes right off the periodic table, and I multiplied. Now in the end, I can also say that this answer is reasonable. If I look at the molar masses, copper's molar mass is a little bit higher than iron. 55 versus 63. So I look at these masses, and I'm expecting a mass of copper that's a little bit greater than the mass of iron. So if I had 6.4 grams of iron, like 7.29, that seems like a reasonable mass of copper. Now another option would have been to calculate the exact number of atoms in the sample. So you could have done something like this, where you said if I have 6 grams of carbon, I could cancel grams and switch it to atoms. Whenever you see atoms or molecules, it's the 6.02 times 10 to the 23rd. Anytime you see grams, it's off the periodic table. 12.011. So you could do this, where now I'm canceling grams and I'm switching it to atoms. I can do this because both of those quantities are equal to each other. 1 mole is about 12 grams, and 1 mole would be 6.02 times 10 to the 23rd particles. So if you plug this in, we're going to multiply across and divide on the bottom, and I'm still looking at about 3 times 10 to the 23rd atoms. And guess what? That's half a mole. And so in the end, I think what's in red and yellow is a little bit less clunky. Nobody likes plugging extra numbers in their calculator and using scientific notation. So if you just keep it at moles and make your samples have the same number of moles, they'll have the same number of atoms. You don't have to switch it to atoms. I mean, you can. Then I would say, okay, I want 3 times 10 to the negative, or whoops, 3 times 10 to the positive 23rd atoms of magnesium. And then I'd want to cancel atoms and put it into grams. You're going to get the same answer, but the red and yellow work is maybe just a little more efficient. And then finally, how many moles of iron are in a 320 gram sample of iron 3 oxide? So I wrote my formula. Iron is a +3, oxygen's a -2. I'm usually a balancer, but if you're a crisscrosser, you'll get Fe2O3. All right, so I took that 320 grams and set up a proportion to cancel grams. I want moles. So I put moles on the top. Anytime I see a mole, it's a 1. Anytime I see grams, it's off the periodic table. So I just did a little sidebar, and I put that mass in my calculator. There's 2 times the mass of iron plus 3 times the mass of oxygen, and I got pretty close to 160 grams. Which then, this starts out kind of making sense, right? If every 1 mole is about 160 grams, I have 320 grams. I got 2 moles. I've got 2 moles of Fe2O3. But the question says, oh dang, how many moles of iron? Well, what I just calculated was moles of this whole thing. It would be moles of iron oxide molecules. Oh, well, they want me to break it down by just moles of iron. That's not a big deal. There's 2 ways you could go about this. I mean, you could just think about it logically and say, okay, well, for every 1 molecule, there'd be 2 atoms of iron. Moles is just a unit that measures a quantity. So for every mole of iron oxide molecules, there'd be 2 moles of iron atoms. Well, if I have 2 moles of iron oxide molecules, then I can multiply by 2 and get 4 moles of iron. Just the iron. So I'm looking at the ratio of iron in that formula. There's 2 of them. Now another option would have been to set up some proportions. You can use this proportion method for all kinds of conversions. Or you could have said, I've got 2 moles of iron oxide. I don't want to know about moles of iron oxide. I want to switch it to just moles of iron. And then I use the ratio from within the formula. There's 2 iron for every 1 iron oxide. Either way, I get 4 moles of just iron atoms.